Let me introduce Team 10, EMAGine.
All right, before we begin, I'd like to give a shout out to all my fellow seniors. We're almost done. Good afternoon, everyone. We are Team EMAGine. To my right, Drew Morris, John Burke, Michael McNeil, and Ryan Hunter. In our presentation today, we'd like to go over the need and applications of our product, our requirements, our overall system design. We'll dive in a little bit with the analog and digital hardware, post-processing software, our current hardware implementation, and finally, we'll wrap it up with any questions you guys might have. So the purpose of our project is to create a device that detects, records, and processes low-level magnetic fields at low frequency. This device must be portable and easy to set up, and will be deployed in U.S. Navy submarines to record magnetic emissions around equipment that are sensitive to magnetic fields. Our device will replace current bulky and non-user-friendly devices, and although the main application is for the U.S. Navy, there are tons of other applications, such as reading magnetic field emissions from power lines, substations, home wiring, and other electronics, and it can also be used for navigation. I'm going to turn it over to Michael for some requirements.
The requirements of our device were that it could detect magnetic fields from 60 hertz to 200 kilohertz. It had to have a sensitivity range of 1 milligauss to 100 milligauss. Had to be easily exportable, basically in CSV files, so that no matter what operator is using, you can open the files. Support 2 auxiliary connections. They're both 50 ohm BNC connections. They're DC coupled with 500 microvolt RMS to 5 volt RMS. And it also needs to operate for 10 days when it's taking a snapshot of the magnetic fields every 10 minutes. Here you can see the overall system design. First, the magnetic field is read by our sensor, and that signal from the sensor is amplified and filtered, and that amplified and filtered signal is sent to the ADC, where it is then outputted to the FIFO buffer, where it is stored until the full reading is taken. There's a 0.2 second reading period where we read 120,000 times, and at 600 kilohertz. And after that sampling period is over, all of that data from the FIFO buffer is stored on the SD card, and it continues over the 10-day period. And then after the 10-day period, all data from the SD card is offloaded over a FTDI USB connection, where the time domain data can be converted to the frequency domain using our MATLAB post-processing. And I'm going to turn it over to Drew.
So I'm going to quickly go over the power. As per our requirements, we had to last on a single charge for 10 days. It also had to be rather small, so we couldn't just get a large automotive car battery and strap our components to it. So what we had to do is we had to consider other alternatives for energy. We ultimately settled on using lithium polymer batteries. They have a very, very high charge density, and they also have a very long lifetime. The other portion of power that we had to consider was we really couldn't inject any noise onto our signal, especially because, as you'll see in the next slide, we're really reading very, very low-level magnetic fields, which then get transduced into low-level voltages. So what we ended up doing for the low noise, rather than using switching regulators, we ended up using linear regulators at the cost of efficiency due to heat loss. So the sensor that we ended up choosing was the Honeywell sensor. The major design challenge with the sensor was the fact that we had a dynamic range of 40 dB, and our frequency range was from 60 kilohertz, or 60 hertz to 200 kilohertz, which is roughly 5 orders of magnitude. And the magnetic field, again, was 40 dB. So if you use a general loop antenna, that is actually a pretty large output and would require more advanced circuitry to help to tune the resonance of the loop antenna to select very, very specific frequencies, and then from there use a different type of amplifier to proportionally adjust the gain. We ended up actually finding a Honeywell sensor, which is actually a magnetoresistive device. It's not frequency dependent, and the way it actually works is it operates in the same general principle as a simple Wheatstone bridge. And so essentially, there is no frequency dependence, and thus the voltage difference between the two pins is proportional to the magnetic field. And it also is able to have a very, very low signal-to-noise ratio, which is also aided by the fact that we aren't injecting a lot of noise by using switching power supplies. So I'm going to turn it over to Wes. Oh, sensor design challenges. Again, so high sensitivity, it can resolve low-end requirements. Again, we had to be able to resolve 1 milligauss signals, and to kind of put that into perspective with everyone, a refrigerator magnet is about 10 Gauss. The Earth's magnetic field is 0.6 Gauss, and so 1 milligauss is very, very low-level signals. Again, because the Honeywell sensor is frequency independent, we were able to not have to worry about the bandwidth. The Honeywell sensor is actually reactive up to 5 megahertz. And again, it was easy to integrate. It's just a resistive device. There is no, again, switching capacitive networks that would tune the resonance to a specific frequency, and then we'd have to have a different type of amplifier circuit to adjust the gain of each resonance peak. Now on to Wes.
Thank you, Drew. So coming from the Honeywell sensor is the amplifier and filter network. The purpose of the amplifier is to take the small, low-level DC voltage from the sensor and amplify it so we can read at the analog to digital converter. The gain is a simple resistive feedback network. And the purpose of the filter is to create rejection for out-of-band frequencies. Again, our frequency range is 60 hertz to 100 kilohertz. The filter will also provide anti-aliasing, and the way we have this is via this chip by Linear Technology, which you see in the image above. It's a 8-pole elliptic filter on chip, and we have an external capacitive resistive network to add that additional pole for more rejection. Some of the major challenges with the design of the amplifier and filter network, first of all, is obtaining a good signal-to-noise ratio. Since our signals, magnetic field signals, are so low, we were really concerned about how much noise was inherent in our system. A rule of thumb that we followed from the very beginning was that we desired a minimum of 10 dB signal-to-noise ratio in order to differentiate between our signal and our noise. A requirement for the filter is that it had to have a sharp frequency roll-off. And the reason for this is that having a sharper frequency roll-off will allow you to reduce the amount of oversampling needed, and in turn will reduce the amount of power consumption in our system. Also, a lot of filters with sharp roll-offs, such as the elliptic filter, they have great sharp cutoffs at your frequency, desired frequency cutoff, but there's ripple within the passband and stopband. So the way we overcame this was that we designed our system to have a maximum of 1 dB passband ripple. Some technical specifications, the amplifier, obviously, as I said, is low noise. We designed to have about 36 dB of gain, which gives us an expected output of 1.15 millivolts per Gauss. Our filter is designed to have a cutoff at 200 kilohertz. Originally, we had our frequency, the higher end of our frequency range to be 100 kilohertz, but we talked to our customers and they wanted us to extend out to 200 kilohertz, so we did that for them. And we achieved a negative 80 dB rejection point at 400 kilohertz. Now I'm going to turn it over to Ryan to talk about our digital hardware.
How you doing? I'm Ryan. I was in charge of the digital data acquisition side of this project that involved the hardware that actually physically acquired the signal. Basically everything after the amplifier and everything before the actual MATLAB post-processing suite. The primary design challenge behind this was developing a device that was both low power, low cost, and still able to maintain a relatively high sampling rate. Due to our filtering, we needed to have an acquisition rate of around 660 kilosamples per second. This poses a problem specifically for the sheer amount of data that's coming across your buses, but also the fact that for each of those samples, in order to attain our 1.15 millivolt per Gauss sensitivity, we would need 16 bits of need a 16-bit ADC to achieve proper quantization. So with all this data, the concerns are, of course, how are you going to store it, which we solved with a flash drive like device, and also we needed to build something that was low power. And of course, actually implementing this were huge debugging problems. We're talking about basically just, a lot of discrete components we purchased off the shelf and threw onto a board. So we had a lot of fun getting it working. Actually, here you can actually see a picture of the data acquisition, the actual ADC and FIFO combination. The purpose of the FIFO was our workaround for the fact that we were trying to avoid using high-end, extraordinarily expensive digital signal processors like a Tiger Shark or going towards an FPGA solution. Using a FIFO gives a way to self-clock data onto sort of a little memory reserve. And each channel, 0 or 5 channels, would have one of these FIFOs associated with an ADC to store the data while data acquisition was going on. So each FIFO had 262 kilosamples of storage capacity on it, which gave us about 0.2 seconds of sampling time. They outputted on a parallel interface, which worked well with the ADC. Their ADC had a parallel output. The ADC helped in the fact that the ADC actually had a busy line out that you could use to clock data onto the FIFO. And both devices had low power down states that allowed us to meet our power requirements. The microcontroller and SD card were nothing particularly special. It was a standard MSP430 that was had enough GPIO pins so that we could interface at least one 16-bit parallel interface. The FIFO actually had a tri-state buffer, which would allow us to switch between different FIFOs. One of the nice features about this MSP430 is it had a DMA, which was necessary for taking a large amount of data off of these FIFOs and clocking it up in a serial link, and saved a bit of time by de-involving the CPU. As far as the SD card is concerned, it was a typical SD card that you buy to store. We had a 4 gig one that we were using. This was our non-volatile memory storage, which was useful both for the fact that it was a cheap way to get a lot of storage, but also it meant that if our batteries did run out in the field, we wouldn't have to worry about losing all the data. The SD card also stored the user settings, things like sampling rate, among other things, were stored in a non-volatile fashion, so you could completely discharge the device and maintain your settings in between operations. So this here was actually a quick little demonstration of this thing's the low noise that this thing actually has. This signal, this was resolving it was a 20 millivolt peak-to-peak signal at 1 kilohertz. This graph cuts off the top of it, so you can kind of get an idea of the scale of those, the noise and how nice it was. We actually were quite fortunate to have a device that ended up working this well in the end. This is the final device, sort of completed. It's a rat's nest, obviously not something you want to stick in a submarine quite yet, but we're getting there. One of the notable things we dropped off was the 5 channels. We only implemented 1, partially due to the fact that we ran out of time, and partially due to the fact that each of those FIFOs is about $100, so kind of broke the bank. But yeah, that was the digital signal processing lab, and I'm going to hand it off to John to discuss the post-processing suite.
Okay, so the post-processing suite is completely designed in MATLAB, and the main thrust behind it is to take the data that I get from Ryan and convert the time-based signal to the frequency domain signal so that we can see the content of the frequency domain. And one of the large goals for the post-processing suite was to make it easy to use and simple to interface. Here's an example of it right here. So it's very straightforward. The top input is the input file, which I get from Ryan. The second one, Mike mentioned that there'd be different periods where it'd be sampling. That's just like, say, take the first period of sampling as opposed to the second or the third. You can put multiple in if you separate them with commas. And the final input is just the name you want to export it under. I exported each window under separate CSV files so that it'd be easy to find which window was where. So if I had multiple windows here, each window would be sequentially numbered. It'd be done1.csv, done2.csv, so on and so forth. And it was fairly straightforward, but there was a couple of issues that came up. The speed of how quick it worked was definitely an issue because it runs in MATLAB. It could easily become very, very slow. At one point, the system took about 15 minutes to run. After shaving off some of the excess, it got down to about 15 seconds. The easy output was important. I wanted the files that came out of it not only to be easy to view, but easy to send to other people as needed. Accuracy was important, and that really lied a lot with the sampling rate and other factors in the processing. And the simplicity was important because I wanted anybody to be able to use it.
So you mentioned the choice of buffer, I think in order to cut costs, but then the actual prototype used very expensive part. What is the end game for that choice? Do you have a separate part that you know you can find, or was it?
Well, I mean, basically it was the availability of dev boards and whatnot, the target chart as well, the factors to it. The Python was pretty easy to get a hold of. It was a little bit more of a debugging challenge. But the primary wall that we ran into with the DSPs is finding a device with a high enough SPI clock to pull in the data. I think even if I was only using, if I was only going to try to simultaneously capture 3 of the channels, I still need something up in the 35 megahertz range for an SPI clock, and that is, you start finding more expensive DSPs.
The other thing important to notice is that we do have to meet the power requirements, and using a DSP chip is going to pull far more current than using a FIFO buffer, especially considering we can put a FIFO buffer at a low power node.
Right?
So how much data do you collect in 10 days?
So it depends actually largely on the user's configuration. You have to set a sampling rate. One of the default standards we were given, I think, was every 10 minutes for 10 days.
At that rate, it'd be 1.7 gigabytes.
All right, so that contributed to the 15 minutes from MATLAB to jump through. Right, to get that much data.
Well, each window can be processed separately, and over, if you're following every 10 minutes, over 10 days, it'd be 1,440 samples. So,
Yeah.
You implemented one channel. If you were to implement all of the channels, would the remaining channels be identical to the one that you implemented?
More or less, at least on the digital side, there's a slight modification I believe in the analog side. The digital side would be the same. You basically have the only thing we didn't have breaking out was a chip select pin that allowed you to select between the chips.
Yeah, so the reason for 5 channels, the overall objective is to resolve magnetic field magnitude vector. In order to do that, you need X, Y, Z components of it. So those are our 3 channels, and we're also asked to support 2 auxiliary connections that will support current clamps that would couple into it. So the only difference between the analog receiver portion, between the magnetic field sensor and the auxiliary connection, is that the dynamic range for the auxiliary connection is much larger, so we need to actually attenuate that signal instead of applying some gain to it. But everything else, from the filter on to the digital, is exactly the same.
The magnetic field sensor that you used was a Hall effect sensor, or was it something different?
No, it was a magnetoresistive device, so it changes its resistance as the intensity of the magnetic field increases.
So how were you able to know that your readings were accurate? Were you able to test the calibrating in some known standard?
What we did was, you talking about as far as like frequency data, things like that?
Well, you take a reading and it says, 0.3 Gauss. How do you know that it's actually 0.3 Gauss and not 0.25, 0.35?
Actually, interesting enough, we didn't actually get as far as to test the amplitude portion of it. What we did do, we did run tests on the frequency by using a Helmholtz coil and a function generator. So we output a known signal, put the magnetoresistive sensor along with the digital acquisition hardware, whatnot, kind of into the mix and see what we got out and debate in action. So
To kind of extend by what Ryan said, earlier in February, once we had settled on the Honeywell sensor and the amplifier circuit, the gentleman at Newark graciously opened up their anechoic chamber to us, and they kind of demonstrated to us how they would go about calibrating the device. And so we actually did receive some rudimentary data based on the generated magnetic fields that they knew were, say, 10 milligauss going into our amplifier, and then we would then take the voltage coming out and use that. And they actually were able to sweep the spectrum, and they provided us with a CAL file. So that CAL file, did you talk about it in your post-processing suite? At the end, you'll actually be able to apply a CAL file to it, which will actually calibrate the output from our Honeywell sensor to the appropriate milligauss signal.
Does your device have temperature sensitivity, and if so, how did you compensate for it?
The AEC would actually have temperature sensitivity. We didn't actually compensate for the design, although the device does have an integrated temperature sensor on the MSP430 that could be used to get ambient temperature. On the analog side.
On the analog side, I'd say everything runs optimally at room temperature. Implementing temperature compensation, that's probably an added feature, something that we can do if we had more time to make a more robust system.
Were you able to use any libraries like NFTW for your Fourier analysis?
It was completely in MATLAB, so the FFTW is what MATLAB uses.
Okay.
So